Okay, we're going to talk about the physical pendulum now. And the main thing that's different between the physical pendulum and the simple pendulum is that, well, this one's physical, the other one's simple. But the physical pendulum is a rigid body that is oscillating versus something like a simple pendulum, which is typically a like a mass or a point mass attached to some string that doesn't even really matter. It's massless, so it doesn't really matter. And then it swings and it oscillates. But a physical pendulum is a rigid body. What that means is basically like, if you took like a metal bar or something. I have actually my keyboard cover. Like, this is my keyboard cover for my keyboard that I have. This is actually like a physical pendulum right here. It doesn't work very well because it's not pivoted properly, and there's a lot of friction between my hand and the keyboard cover, or the keyboard like wrist mount. But you can kind of see that it swings almost like a pendulum because I'm pivoting it up here. So then, whoa, 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 right? Okay. It works better if you have a more frictionless pivot. My fingers don't have a lot, have a lot of friction, right? Um, I just want to remind a couple of equations. This is Newton's second law, F equals ma. That's pretty basic. Also, torque is equal to RF sine theta. Okay. So that's what I'm going to do. Okay. Now, or you can say, if you really wanted to, RF perpendicular to uh, the um, the R vector. Doesn't really matter. So is that. Okay. The physical pendulum, in order to do this, let's see, this pendulum, so if you actually look at this example, you'll notice that this is actually not a uniform board. It's not like just like a straight rectangle. It's like maybe like an oar of some sort, where it gets longer as it goes, or sorry, it gets wider as it goes, right? So what I'm going to start with, okay, is I'm going to start with my basic torque equation, which is torque is equal to torque net is equal to I alpha, okay, and then the torque net, the only thing that's actually applying a torque, so mg cosine theta does nothing for the torque, okay, because it points directly away from the axis, but mg sine theta does. So I'm going to do mg, I need to do the distance times mg sine theta, right? So, or yeah, distance times mg. Well, it's a distance d away, okay? So it's going to be d mg sine theta. Now this is actually going to be negative because the force, again, opposes the displacement. I'm going to set that equal to I alpha. Wait, but alpha is actually the second derivative of theta, okay? Interesting how that works out. Hey, wait a minute. I'm starting to see the vision here. I'm starting to see the vision. Okay? You start to see it? You know why I did that? Because I can. So the reason I did that is because I want you to see this, okay? I want you to see this. If I divide I on both sides, I end up getting d squared theta over d t squared equals negative dmg over I sine theta. Wait, really quickly, this is where does it say? Oscillations are small. Sine theta should be theta. Okay, so this is just going to be d squared theta over dt squared equals negative dmg over I times theta. Now that right there is the simple harmonic motion differential equation. Okay, we did it, right? I've said it a bajillion times. Well, I can now figure out what omega is, okay? So from this right here, omega has to be, negative omega squared has to be negative dmg over I, okay? And then, let's see, if I drop the negatives, okay, that becomes omega squared equals dmg over I. And then if I root both sides, I will get omega equals root dmg over I. Okay. Now, I also remember that omega is equal to 2 pi over t. Okay. So that's exactly what I'm going to do, is I am going to now use this equivalency right here. Root dmg over I equals 2 pi over t. I'm going to flip both sides because I can do that. Okay, so t over 2 pi equals root I over dmg. Okay, and then multiply both sides by 2 pi, and you should end up getting the period for a physical pendulum is equal to 2 pi root I over dmg. Okay. Okay. All right. That should be it, really. Okay, D, M, G. Okay, good. And I guess this would actually be I sub D, right? Is the moment of inertia for this. And you just have to remember the moment of, or the parallel axis theorem, which is that some distance from the center of mass, you have a different rotational inertia um, than you do at the center of mass, or with respect to whatever, right? And that depends on the object, okay? Um, okay. All right. Good. All right. Cool. 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 That's the physical pendulum. I'll be right back with the torsion pendulum.